v by 2. So it should be at least connecting half of the nodes.
Yeah.
So, and if you have two paths where you can connect half of the nodes, then there definitely has to be a common one, otherwise you will exceed
Right.
the total.
So that's the first step. If I have two paths, they can't be disjoint. Because two disjoint paths means too many vertices. If they have no common vertices, v by 2 plus 1 plus v by 2 plus 1 separately, that's too many. But that's for two.
Yeah.
Is it possible that if I look at the paths from S to T, another path intersects here, but a third path doesn't go through here. Goes here, then here, then here, then here, then here. So I have three paths, but they don't really go to the same point. They all intersect pairwise. Path A intersects path B, path A intersects path D, path B intersects path C, but all A, B, C don't intersect in one point. Is that possible?
My way of saying it, like if you have a path of 5 nodes, so there is only so many number of, I think, 2 or 3 extra nodes which you can use for the other paths. Because if you go on increasing more the number of extra nodes for the other paths, then this path becomes, the main path becomes one.
So I agree that if I have two paths, they must have a good intersection, like I said. So you say the second path must intersect the first one.
No, I'm saying any other path, like if S is the main path, then you have T1, T2, T3, so many other paths. So if S is the minimum path, if it has like 5 vertices, then if you want to make sure that everyone has, if this path is valid provided you add all the other paths, then there's only certain number of extra nodes which you can use other than this 5 nodes to still keep this path up.
Right, so I have to use, because all paths are long, right? You say this, he's saying this is the shortest path from S to T. So this already uses half of the vertices, or more than half. Any other path, it has to be long, because that's what the problem says. All paths are long. You can't have a short path. So he's saying there's not enough vertices outside, so any other path must intersect a bunch of those. Maybe the other path goes like this, and then goes like this. That's another path, right? And then maybe there's another path that also has to use a bunch of these, right? Maybe it goes like this, and then it goes like this, and then this. I don't know. Why is it absolutely necessary that all those paths pass through one vertex? I know intuitively that makes sense, but how do we argue formally? In fact, I have a generalization of this problem, which is a good final candidate, you know, which says, suppose all the paths have length 1 by v times k. So this k is not 2 anymore. K could be 2, or k could be 3, or k could be 10. Then I want to show that there is a bottleneck subset of, what is it? I think it's k minus 1. What I mean by this subset is B, bottleneck, is included in B. It's a subset of vertices. The size of B is at most k minus 1. And any path passes so this is exactly your problem if k equal 2. If k equal 2, it says all paths are 1 plus v by 2, and the bottleneck has one vertex. Everybody must pass through that one vertex. The more general problem, it's saying the bottleneck B maybe for k equal 4, it says the bottlenecks must have at most 3 vertices. There are 3 vertices here. And any path from S to T, right, must pass to somewhere in B. There's no way to avoid this B. Think about police is chasing a bunch of people who robbed the bank. They have to check a lot of points in the city, right? If all paths are long, it means police only need to check a bottleneck points like the airport, the train station, and the harbor, or something like that. Because there is a bottleneck, all those paths must pass through one of these 3 points. So if I check up those points, there is no exit route that can avoid this. That kind of example. The same thing can happen with packages on the internet. If all paths are long between here, paths of routing packages to the internet between here and India, all paths are long. That means there's a bunch of bottlenecks, bunch of 3 or 4 routers in the world that if I manage to control those, I control all the traffic from here to India. Because all traffic must pass to one of those 4 points. Those would be the cables under the ocean, probably. If I manage to control those 4 points, in fact there are like 3 cables right now in use, 2 under the Pacific, 1 under the Atlantic, right? If I control those, I control all the internet traffic. I mean, there's satellite traffic, but that's not used commercially. Okay?
So here is the last vertex of intersection is V minus this whole term.
What?
The last node in that path where all the paths will intersect is V minus this whole term.
The last node, what, all intersect or some intersect?
I mean, when every path passes that particular intersect, that particular.
So that's for k equal 2.
Yes.
For k equal 3, I have each path passes to one of those. Right? So what I said at office hours for some of you was that there's 2 ways to think about this problem. I think one way, which is very constructive, is to think if this is the shortest path, that's a canonical path. So that's my line path. I'm gonna note all the intersections. Every other path must intersect somewhere, right? So I'm gonna call Fi, this is the path I. F means first intersection of this path. And maybe if this is path I, this is last. This is the last intersection of path I. So every path intersects somewhere, because we already said that 2 paths cannot be disjoint. Intersect somewhere, and then maybe intersects a few times, and then it has a last intersection point before it gets out and doesn't intersect until T. So now, if I have a different path J, that would be Fj, the first time J intersects, and this would be last J, the last time J intersects. What you should think of, if I only look at the shortest path, I ignore the other paths. Where are these F and L points on the shortest path? A bunch of F's and a bunch of L's, right? And how do they look like? Maybe that's where we start this idea with disconnecting the graph. I don't know. The other hint, if anybody solved this problem? What's the other option? Is to look at BFS. Suppose I do a BFS from S towards T. Look at those waves. BFS works in waves, right? Nodes reach the first wave. That includes only the ones that are directly accessible from S. Second wave are the nodes accessible from the first wave, but not directly. Third wave accessible from the second wave, but not from the first wave or directly. Look at those waves and see what do you see. In those waves. Like how does the graph, the nodes of this graph, like this would be the first wave, right? There'll be a second wave that's reachable from the second wave, and so on and so forth. And at some point there is the wave T, right? There is at some point BFS reaches T. So you should ask questions like how the nodes are distributed over waves. How many waves do I need till I reach T? Things like that. Ask yourself those questions. And see then, either this approach or this approach, can you make it work in the general case? Where I don't have k equal 2 and the bottleneck 1, but k could be 7 and the bottleneck must have at most 6 nodes. All right, so let's move on. There is an exam, right? Saturday, April 21, exam. Can you make it? I hope you make it. So a quick recap, what do we have? Shortest path, single source, shortest path. What was the idea? So we had a path, and we say to discover the path, shortest path, we need to relax edges in path order. So there's a theorem that says if you relax the edges in the path order, you discover the shortest path. So one way was brute force. What was it? Right. Relax. There's a loop v times, and then relax all edges. Right. Bellman-Ford algorithm that was saying if I relax all edges, I'm sure I'll relax the first edge in every path because I relax all of them. And then when I relax all edges, I relax the second edge in every path, and many others that I don't need. And then I relax the third edge in every path, and many others I don't need. So that's why I'm sure all paths have been relaxed in order. Or we can have what? Dijkstra that says two things. The minimum ESP, that's the estimate the shortest path, is actually correct, the shortest path. And then proceed from there. If you know a node is already relaxed, or it's already discovered shortest path, I can relax edges from that node, because that way I know I'm not wasting my time, because it's already, right? If everything so far, this is the min ESP, which is actually the shortest path, so I know this one's good. Then I can take all edges from here, relax them. That will be in the order of the path. And then, that was the single source. We have all source, shortest path. That is, this is a fixed S. All the paths I care about here was from a fixed source. In here, I want all the paths from everywhere to everywhere. So we say CUV is the shortest path from U to V. That's our goal. And the one that we did last time was to think of this as we're going to add a parameter m and say CUV is the shortest path from UV using at most m edges. Because we construct this little by little, right? It's so, like if m equal 1, it's very easy, right? What is C1 of UV? What is the shortest path from U to V using at most one edge? If there is an edge, right, it's, let's say, the weight UV, that's the edge weight. If there is one. and it's maybe plus infinity if there is no edge. In fact, in shortest path problems, when we don't have an edge, we call it plus infinity, or minus infinity if we want to go the other way. So it's a way to say going this way is impossible. So if I only want one edge, it's either that edge or nothing. So how to expand from m edges to m plus 1 edges, right? So if I say, I've already got all the shortest paths that use at most 3 edges. Now there might be some better paths that use 4 edges. So I need to expand from 3 to 4, right? How do I do that? Well, so how do I go from m to m plus 1? I said before, I'm thinking of a path. Here's a u, right? It goes somewhere, and there's an intermediary t here. And I'm going to say, if I want this path to have at most m plus 1 edges, that's what I want now, then this path must have at most m edges. This is 1 edge. So I'm saying Cm plus 1 of uv, it's either passing through some node t, right? So that would be Cm ut plus this edge is weight PV, right? Or, so that would be, I have to do at most m plus 1 edges, and I have to search for t, right? I wouldn't know who t is, I need to search for it. So I need to try multiple t's, like in dynamic programming. I don't know who this t is. Or, I could go through the old path. Just go from U to V like I knew how to go before the M step. Like I'm building these C's by M, right? So it's first C1, then after C1 I do C2, after C2 I do C3. So I already have Cm. I could say maybe the best path from U to V, even using M plus 1 edges, might be only using M edges, right? The shortest path might be obtainable with M edges. So it's either what I did before this step, or trying to combine the before step plus one more edge. Now there might be things that are included in both here, right? Because this might actually, is not guaranteed to have exactly m plus 1 edges, right? This is saying what? It's the best you can go from U to T with m edges or less, plus that last edge. But that doesn't mean totally, because it's at most m, right? It could be less than m, and then the whole path is less than m plus 1 edges. But that's okay, even if I have included two things here, I'm not trying to count everything once. I'm trying to find the what do I need to put here between those two things? Minimum. So I'm trying to find the minimum. If some of them are included in both cases, I'm just doing more effort, but I'll still find the minimum out of them. So this in here has to be minimum for t. I don't know who this t is, so I have to try a bunch of t's and see if I can get something that beats my previous way of doing it. So then I told you something that this like that, naively, will take a lot of time, right? How many for loops I have here? 4. There's a for loop that goes through the m's, 1, 2, 3, 4. UV, when I update something, that's a square because I have to update every cell. And each update includes a search for t. That's another search for all possible t's, right? So there's a 1 loop, 2, 3 loops because I have to do all pairs UV, and the 4th loop. Who's with me here? Okay. So it's n 4th. And now this is done in the book in detail. So I say, you know, intuition, but this is not rigorous. So this is naive time, V4, because n here is the number, the vertices, right? Now, if I don't want to do this rigorously, I just want to create an intuition. I want to think of this Cm plus 1 as a matrix. It's Cm, the previous matrix, with some sort of operand. I'm going to call this, you know, like SOR or something, some new symbol. The W is the weight matrix, right? So WUV is the edge from U to V. So now this operand is not the typical operand that we've seen with matrices. It's not addition or multiplication or something like that, right? This operand means this is the minimum between the Cm and Cm plus some last edge there. So if I look at this as an algebraic form, I'm ignoring for a moment what this operand does. It does this minimum. It says either what you had before or try a new edge. I'm going to get that, think of it inductively, right? By C of 1 is pretty much the edge, right? It's something very similar to the edge matrix. And then C2 is kind of this operated with itself, right? And then C3 is what? Something like that, right? So this looks like a matrix multiplication, except the operand is not multiplication, right? So I could say Cm is probably this at the power m, but power is not multiplication power, is this operand power. It's like, do that operation with itself n times. And for matrix multiplication, there was a trick. That was saying, when we multiply a matrix with itself, we don't want to do times itself n times. Instead, we do repeated squaring, right? So we do w squared, then fourth, then 8, then 16th, and then we have to pick the right powers to multiply, right? So we try to do the same thing here. Let's find a procedure that does, how can I do this? Like, I want to do something like, instead of doing this, I want to move into C, like repeated squaring would be something like C2 to the m. Sorry, C2m. It's kind of like Cm operated with Cm, right? That's how repeated squaring worked. You get C1 is W, then the next step is C times C1, that's C2. The next step would be C4 would be C2 times C2, except it's not matrix multiplication, right? So this way, I'll do it. I'll have to increase m, right? M equal m plus 1, right? So is that correct, or is 2m? So after m is 3, no, after m is 2, I get C4. What's the next m? 8. So that's m is 2m, right? And I do this while m is smaller than how many? How much do I need to go here? The maximum m that I need. That's the maximum number of edges in a path. V minus 1, right? So as long as this is less than v, I keep doing that. So this is clearly a logarithmic progress. Sorry, exponential progress, right? Because before I had to do this loop v times, this is going to be log of v because at every time I do square. There's another benefit to it. That is, in actual repeated squaring, if I need to compute w at power 100, I have to decompose 100 into the square powers to see which ones I need to multiply at the end, right? So what was it? W at 64, 32, at 4, right? In here, I'm going to argue that's not necessary. You can overshoot it. Suppose I need 100, but I just do repeated squaring until I get to 100 or more. I'm not going to get 100, so overshooting means what? I get instead of what power? I'll get 128 instead of 100. So what I'm saying is, once I do this repeated squaring, I don't need to do these powers of 2 exact, because I need C at V, right? But say I don't do that, I overshoot, and I get overshooting. I'm gonna get C at not V, but some power of 2, right? With the property that that power is at least V. So if V was 100, I'm not going to get 100, I'll get 128. Is that a problem? What will be that? Yes?
With increasing numbers, the difference will be exponential. Like after 1128, 2048.
Right, so it's much bigger, could be much bigger. But in terms of computation, it saves me the part of figuring this out, right? I'm asking if this is correct. Who would be the C at 2p of uv? Back to the definition. Will be the shortest path from u to v with at most how many edges? 2 to the p edges. I say that's the same as CV. So it's true that I overshoot it, but the values, the cells inside C didn't change. That's not true when you do multiplication. When you do multiplications, if you overshoot, you multiply more W's, right? Unless W is the identity matrix or something like that. When you multiply more W's, you're going to change the values. In here, I'm saying, even though we overshoot it, instead of C at index V was 100, now we got C at 128. Actually, the cells didn't change. They're still the ones we need. Why is that?
Because there is no new path which is being added after.
Because no path, no shortest path will have more than V edges. Why is that?
No negatives.
No more parts.
Why is it that the shortest path cannot have more than V edges? No negative cycles. If a path will have more than V edges, must have a cycle, right? Some nodes will have to be repeated. But for that path, the shortest path to include a cycle, it means the cycle overall weight is negative. Otherwise, the shortest path will not include it. Well, what would be the point of including a positive cycle? It's just increasing the path, right? So if I have a path, and then I could go into a cycle here, right? If the cycle total weight is negative, that would decrease the path, but that's not possible. We said in all shortest path problems, they're ill-defined if you allow negative cycles. And if the total weight of the path is positive, that's allowed, but then the shortest path will not include it, right? So my argument is that even if we overshoot this, we just go until it's bigger than V, and it's not exactly V, the cells inside the CUV are not changed. They're still the ones we need, the actual numbers there. Now that doesn't include the tracking. Like if I don't just want the value of the path, but I want to see, okay, I need you to output the actual path. I have to figure out dynamic programming. There's got to be a way here, you know, who is SM or SM plus 1 UV, right? you need to have some sort of tracking. If you change the path, you need to keep track of something to know how to recover that path. Because like in dynamic programming, C only stores the objective value, the length of the path. So from C alone may be hard to recover the path. So I need some tracking to figure that out. Now, what I didn't explain here, what I want you guys to go and read it from the book. How does this actually work? Right? I want to replicate the matrix multiplication idea. I think everybody understands that because this is times W or operand W, it's effectively, if I could do this, instead of doing one at a time, if I just do two at a time, it will work, right? The question is, how does this work? Is this correct? Instead of operating CM with W, which is what we have right there, this is the W operation. Can I do C1? C1 with C1 will be correct, right? Because this is C2 is C1 with C1. C1 is W. But how about C4? If I say C4 is C2 operated with C2, is that going to give me the correct C4? Which is who? Who is actually supposed to be C4? C3 operated with W, right? So what I really want is C4 to be C3 operated with W, which is who? C2 operated with W, operated with W. That's what I really want. And instead I'm getting C4 is C2 operated with C2. That's the same thing. I know W operated with W who this is. That's C2, right? So I need to prove some sort of algebraic notion of this operator like associativity to say that if it's associative operation in a topological algebraic sense, then this thing will work out. So this is a good exercise. Let's go. It's in the book, well detailed. Why can I do this operation just like I did repeated squaring? Now, the most important thing here is to remember the idea. This repeating squaring idea applies to all kind of operands in rings and groups, like high-level linear algebra. It's not specific just to multiplication. So if I do this, what did I get? How my running time changed. I had 4 loops before, right? 1, 2, 3, 4. This is a 4th loop. And now I have what? 3 loops. The search remains. This remains. But this loop, instead of being a linear loop, it's now a logarithmic loop. So what's going to happen? Okay. All right. There's a better way to do it. So my real purpose for doing this, right, is to practice more dynamic programming. Right? I really love dynamic programming. So your exam very likely will include the dynamic programming question. I say very likely as in I can't say guaranteed my life, but in the past 10 years, the final exam contained a dynamic programming question. Okay? And 2 or 3 graph questions. That's guaranteed. And there will be a double start problem, right? Like one problem that if you solve it, you can get a job at Google. No, I'm kidding. That's just for the midterm. It will be an additional problem that's not necessarily graphs, that's not necessarily dynamic programming, but there will be no 2 double start problems like in the midterm. That's for sure. Okay, we want to have a realistic exam, not a brutal thing like the midterm ones. But this is not the most efficient way of doing it. So I wanna do 2 things with this. Practice dynamic programming, because that's good. And I want you guys to think about this operation. How can I make an operation that's not even an algebraic normal operation? It's this minimum between 2 things. I mean, it's a well-defined what it does, but it's not a plus or multiplication or say subtract this from that and add some multiply by 3. It's a minimum type of operation. So how come this works in this form here? Okay. So the right way to do that is to think about yourself first and then read it from the book, see if it makes sense. If you read it from the book first, it'd be too biased. It will force your thinking into exactly how the book is written. I think the right thing here is to try to figure out for yourself, maybe talk among yourselves or something, and then, okay, when you think you have it, read it from the book to see how it's being done. The most talented students in the previous years, people who really want to go for PhDs, they try to implement it before reading it from the book. It's 3 lines of code, really, right? Can you implement this method in a programming language like Python or Java without reading it from the book and see if you actually get the shortest paths with a fancy kind of repeated squaring method? But there is a better way that has a name. I forgot the name. Floyd Warshall, maybe? Something like that. So what says is we'll do dynamic programming. The reason we do dynamic programming is because, like I said before, there is a very, very strong optimal solution structure here. I think that's pretty clear that if this is the shortest path from U to V, this gotta be the shortest path from P to V, and this gotta be the shortest path from U to V. It's very simple exchange argument. If there's a better path, I replace that and I get a better path overall. And that has to happen for every single intermediate node T. So that gives me a lot of power of how to break this problem into subproblems. Every single node can act like a breaking point. Right? So instead of doing it by edges, I want to do it by vertices now. So I'm going to have my C of M UV, which is the shortest path from U to V, using at most not M edges, but M vertices. Right? So it's like growing it up again, right? And I'm looking at the vertices now. So how can I do this? So I need now to figure out this part here. So if I restrict T to be the last vertex in the path, like I did in here, T was the last vertex, right? I'm going to end up with the same recurrence kind of by edges, because what I'm really controlling here is the last edge. If I say T in there is the last vertex in the path, then I'm going to end up with look for that T and find the edge. Right? So I don't want to do that. I want to allow T to be whatever. Right? And I need to say, here's another path, right? Let's say this is, this in here, this path is C M of UV. And this in here, let's actually, let me draw this again. This is the concept. So what do I have? U, V. I could either go directly with what I have. This would be C M of UV using at most M vertices. Or I could go to some T, right? This is paths. I usually draw edges as straight weights and shaped ones as paths. How can I define, how can I say what I want to say, but I don't know how, is this is C M minus 1 of U to T, right? And this is C M minus 1 of D to V. But that's not like, what's the problem? If this is, what does it say? You can use at most n minus 1 vertices to go from u to t, and this is saying you can use at most n minus 1 vertices to get from t to b. That's not going to be what I want now, right? This whole path. Okay, how many vertices are there? Too many, right? I wanted to get n plus 1, and this can have too many. So I need to find a way to think about this problem. I want to go by vertices, using at most vertices, intermediary, but I don't know how to break into subproblems. I could choose t to be the last vertex, so then it's whatever I had plus 1. But then I think I'm getting exactly this thing that was in here. If I do that, I'm going to get exactly this property here. So I need a way to control these vertices. Just controlling it as a subset. This is saying what? The set of intermediary vertices as a set. It has to be at most m, right? That's what the property is saying. The vertices you're passing through, it's at most m. Problem is, I don't know how to control this set. So I try two things. This way, I don't get the property optimal substructure broken the way I want. And if I do this way, I'm doing it effectively by edges. So I need an idea. Middle means?
M by 2.
So if I do a t here, right? What he's saying, let's say you allow at least n by 2 vertices on this side, and at least n by 2 on this side. Right. The problem is, so is it true that every path can be broken into some n by 2 and n by 2? That's true, right? I have to search for the t. But what about here? I don't have control over what vertices are here. How do I search for a t? I mean, to search for this t, if I fix a t, I say, I'm going to try every possible t. Right? Once I fix a t, so let's follow this idea and see why it doesn't work. What am I going to tell the vertices allowed here? There are at most n by 2, but I have to exclude this t, right? Because t cannot be in here. And what am I going to do here? I'm going to tell them there's at least n by 2, and I have to exclude the t, and also exclude this other side. How can I control? This is not the previous problem I solved, right? Because it has this additional constraints. You can't use the same vertices that were used before. That's a much harder problem. Do you remember any problem when I had this? Once I break it in half, you can't use the same items like the other half? Right? So how did we solve the controlling problem or the items in the knapsack? What? One. How did we solve that problem? We chose an order. Now the order was not important which order it was. It was only used as a fixed global order for control. We could choose the order to be a random one if we want, as long as that's a global order that controls the item set. What's good? So how do we apply this here? Say I choose an order V1, V2, V, right? There's V of them. So let's say I have the item subsets like in the knapsack. Who was item K in the knapsack? Item set K. This controlling order allowed us to not have all the subsets possible. That's an exponential number of subsets. But instead, what were the subsets we used in the knapsack? Where up to V1, V2, up to Vk in that order. So I don't have an exponential number of subsets here. I only have V subsets. So I have to change this definition using at most m vertices. That's not good. Doesn't work. I say using only vertices where? In so I'm not going to say use at most m, any m. I'm going to say use only vertices, let's say m here, from 1 to m. So again, I fix this order that's random. This is only for purpose of control. And I'm only telling here Cm is the best path from U to V that's allowed to use as intermediary vertices. Of course, the U and V are fixed. It's whatever the path is from there to there. But intermediary vertices are only allowed to be V1, V2, up to Vm. So who is, in this new definition, who is C1 of UV? First of all, who's C0? 0 is not allowed to use any vertex, which means what? Is the same as there is like W, right? It's only direct edges. If I'm not allowed to use any intermediary vertex, this is just direct edges. If there is an edge, that's the path. If there's no edge, I have no path. But who's C1 now? I'm allowed to use who as an intermediary vertex? V1 only. So now this is so from U to V, I don't think you guys can see here, right? From U to V, I can go direct. Direct is still allowed, right? Because it says using those vertices doesn't mean you have to use it. It means you can use it, right? Or I could go now intermediary through. Has to be a direct edge, right? Why? Why can't it be a path through other vertices? Because I can only use V1. So I say at C1, you are allowed to use either the direct edge or going through V1, but only V1. How about at C2? What's the situation at C2? I can use the direct edge, or I can go through V1, or I can go through V2, or I can go through V1 and V2, or I can go through V2 and V1. So I can use this V1, V2 in any way I want, right? I can take any path from U to V that passes intermediary through V1 or V2 or both of them. So what's going to happen at C3? I can now use V1 and V2 and V3. Right? So C3. Let's write this in a different way. It's either the direct path, which is edge UV, that's direct, or it's C1 of UV. That means V1 is intermediary. It's not necessary to be, when I say intermediary, means the paths are allowed to pass through V1. Or it's C2 that says V1 and V2 are intermediary. Or it's C3, which is V1 and V2 and V3 are allowed as intermediary. Now, of course, the way I wrote it here, C3 includes these other options, because when I say V1, V2, V3 are allowed, that means I could just use V1 or V2, or I can use V1, or I can use none of them. So how do I write this as a recursion now? there's really two options like in knapsack. I want to think of these possibilities really grouped into two main options. I can either use V3, the intermediary node V3, and then if I decide to use it, how things is going to look like. I have to go from U to V3 and then back to V. And what am I allowed to use here? I can use V1 and V2. So this is really C2 of U and V3. And what I'm allowed to use here? I can still use, sorry, this is, yeah, to V3. This is from V3 to V. The problem so far is saying, is this correct? So I have this solved as a subproblem already? I do. I have this solved as a subproblem already? I do, right? Because C2 will be computed before C3. Everything that has C2 will be computed before I move to C3. But there is that thing that says the vertices that I use here cannot be used here. Right? Is it possible that the shortest path, but is that a concern? So suppose I allow it to happen in my recurrence, and I want to check if that's somehow inconsistent. Is it possible that the shortest path passes to some node K, or let's call it T, and then this shortest path passes to the same T? Can that happen? Can I have a common node here, T, that the shortest path would use that T, and then the shortest path here would use that T again? That's possible, but this wouldn't be the shortest path. If there's a common T here with here, that, I'm not saying that's impossible. I'm saying then there's no way this will be the shortest path, because I should shortcut at T, right? I shouldn't go around. It's something that requires some thinking, right? Imagine how many interesting problems can be made with this T, this little T that's in between. It's the cause of all pains with the shortest paths from now on, right? This T is a very interesting T. If there is a T, something happens, right? So I can use V3. In this case, I have what? The way to go from U to V3 plus the best way so far to go from V3 to D. Or do not use V3. It's like in knapsack. I choose not to pick the item K, the last item. In each case, it's C2 from U2. And of course, between them, I choose the minimum. Because it's the shortest path. I choose the best option, meaning the shortest path. Now, this is incomplete dynamic programming. You guys have to finish it up. There's tracking here, there is bottom-up computation, all of that, right? But that's pretty straightforward because it goes just like before by these levels, this index of the C matrix. And I don't have to worry too much about computation table. Like it's obvious there is a good order of computing the problems. If you do C2, if you have the entire C2 computed, there's no problem in doing C3 in any order you want, right? You can pick any UV and just do the computation because all the subproblems are solved already, right? So this which UV you pick to do the C3, it can be in random order, assuming the whole table C2 is already computed. And remember, I have to use the knapsack trick that says, okay, the vertices are in fixed order, which is the order I pick in advance to be random. And if I do this, I have to loop it, right? This would be a loop over M, right? And this is really M plus 1. M, V, M plus 1. And this is M again. So I have to loop it from M equal what? 1 to D or something like that, right? Because I have to do C1, C2, C3, up to all the vertices that I get down to V. So how long, how much computation is here? This loop is linear, right? And inside each linear loop, I have U and V, that's a pair. And inside each, now I pick the M, I pick the UV. How long does this take? Do I have to search for anything here? Is like before I have this T that I had to search for it. I didn't know which T to use, so I have to look for all T's. In here, I know who Vm plus 1 is. Is the next V in that order. I'm not looking for it. The order was picked globally initially, so the order never changes. It's a global order, right? Again, it doesn't matter that order. You can pick a random order as long as that's a controlling order. So Vm plus 1 is well defined by M. I don't need to search for Vm plus 1. So how long would this take? So then the whole loop would be? This is Floyd. What's up, Leonard? Remember to finish up. I mean, I like those questions. How do you trace now the shortest path back? It's not hard. This is the kind of tracing we did for dynamic programming. But remember, C only keeps the objective, the value. How big or small was the shortest path? It doesn't tell you which are the intermediary vertices. So if I decide to update, this is my previous shortest path with M, with only up to M vertices. If I decide to update to say, okay, I found a better path going through the intermediary vertex Vm plus 1. How should I update the tracing? What should I keep track of? In here, if I want to say Sm plus 1 of uv, that is keeping tracing, in this case, when I update, what should this be? What do I need to keep track on? VM. So conceptually, what can I keep track on? In the previous one, with by edges, I keep track of that T, which was the last vertex on the path. It says if you want to go from U to V, S will tell you that before V, the last vertex you pass through is that T that you search for. In here, what should I keep track on? The last vertex in this order that has been used. So in this case, what if I decide to update? What is the highest, the last vertex in this order, fixed order that has been used? This is using Vm plus 1. So I need to keep track of V. What is the highest order V that's being used? So are we following this? In here, I had the highest order being used between U and V, which is not necessarily Vm. Just because this is Cm, the Cm is saying you can use up to n vertices, but S has to indicate exactly which one was the highest V that has been used. Every time it's an update, I update because I have to, this clearly says I have to pass through Vm plus 1. So the highest order V that being used is Vm plus 1. But before may not have been Vm, may have been V4 or V5, right? Because some of these operations did not update, keep the previous paths. So if I have this S, how do I print the solution? Somebody says, I want the path from U to V. What do I do?
Don't we also need the M to be stored?
This M, I mean, this is gonna be stored as the index here, but I don't think we need this. This, I don't think we need it, this exponent. We just store one S, I think. Let's figure out if I have this, how do you print the solution? We have U and V, and then S of UV is gonna say what? Which V to use? So I says, you know, you gotta use this V. So then I decided to use this V17. Then I do tracing now between who and who? I do tracing between those two. And that S will tell you, okay, you need to use V. In here, there will be something. Can this be V19?
No.
It can be based on the order.
So again, this came out at V17. Can this between, can be this V19?
Placing the order is
Order.
to like the random
I'm
order.
saying,
We can.
how would you trace solution if you have this S? You say, look at S of UV, that tells you the highest order is V17, right? Then you're gonna trace between U and V17, right? Because you know now the path passed through V17 somehow, but you don't know where V17 is in the path. In the previous dynamic programming, we knew exactly that T is exactly the previous vertex. So that's just a simple edge here. In here, we don't know. Now, if I trace between this, can I get V19 here?
No.
Okay. So I get V12? Is that it? But that will force me to always output a path that passes these vertices in that global order. That seems incorrect. Once I pick a random order, it can't be that all shortest paths follow that random order, right? That's absurd. So how? Maybe we messed it up. Wait a minute. This is V12. Can here be V16? Can I have V16 in here? Uh-huh. So I don't have necessarily that random order, right? I'm making a little bit of a confusion here because I want people to realize this is not a trivial thing. You need to sleep on it. How do you actually trace this solution, right? And then I'll have to call recursively now between here and here, right? Recursively between here and here to recover the paths. So my opinion is, just figure it out, I don't need to keep track at every M. I just need to keep track globally, so far, what was the highest V used. And then if later on, at the next step it updates, I'll just erase Vm plus 1 and I put some higher V. That, I think, concludes our shortest path discussion. There's more interesting ideas, but yes.
So question, so we introduced that another way to solve that is because that in the previous one, we think that there's a common vertex in the left and in the right. And then we prove that there is no common vertex on the left and the right. So,
The previous one by with that T, or?
yeah. Yeah.
So in here, we really go by the edges.
No, I mean, using that one in that graph.
Right.
So you said that there may be a common vertex, like in the discrete snapshot, right?
Right. So the left side and right side,
Yeah.
if they theoretically, if we allow a common vertex,
But then you prove that there is no common vertex
Right.
because there is a short.
Right.
So.
why is this method incorrect then? Is that?
Uh-huh. No. I mean, why? Because the reason you introduce another algorithm is.
No. The reason we introduce another algorithm is because this is faster.
Oh, okay.
This is V3, and that even with the matrix multiplication optimization is V3 log V. The main difference is not that one allows common vertices and the other one does not. I said that to force you to thinking into, okay, what's going on this path, what's going on this path. Even if we allow common vertices, they will not happen because the shortest path cannot pass here through some vertex V3 and again here to V3. The path will just jump from V3 directly. But this method here essentially go by asking common sense English, what is the last edge that's being used? That is the main mechanism here. It tries to figure out all possible last edges because it goes through a bunch of T's and say, what could be the one that gives me the last edge? Last edge is equivalent to asking, what is the last T in the path, right? Because the last T node creates the last edge. This one is not asking that. This one is very similar to knapsack. It's asking what? Which vertex in this order is the last one used? So if I say it's V17, it means what? I'm not using anything after V17. So it's kind of saying, if you have the following hubs to pass through, and they are sorted, you are only allowed to use up to hub 17, not any further. So the mechanism following this, it's somehow in dynamic programming sense close to the knapsack. The mechanism following this is more close to the rod cutting problem. If you want to chop off that wire to sell it, well, how much can you chop out of it? In here, it's necessary to search. The main advantage in running time is that in here you have to search for this T, right? In there, we don't have to search because every time we move on, we know exactly what vertex we can use as intermediate. Okay. So that being said, we're done with shortest paths. Many problems in the industry with shortest paths. In all these mapping problems, everybody's using now maps and give you the routes and traffic and all that. And if I have traffic, I have a much more interesting shortest path problem, right? The edges are static edges, which is the distance, perhaps weighted by the road type. If it's a highway, even though it's a distance, I know people go faster, so I have a notion of speed. But when I take traffic into consideration, those weights changes the speed value, right? Even it's a highway, it might be, you can't get 60 miles an hour because it's traffic. So now you're Google, and you know how to solve shortest path problems, I'm sure, right? Google knows how to do that. They must have some people who do that, right? But now you have traffic conditions. So how do you include the speed or the traffic? Traffic doesn't change the distance. It just changes the slowness, the what the speed you can get on that segment, right? So how does Google estimates traffic? By now, I think everybody knows, given the latest scandals with Facebook and the previous scandals with, what was it, NSA, and the previous scandals, that those companies spy on you, okay? I mean, it's just, you have to accept it. There's no real privacy. If you have a phone, you get spied on. Most people knew this before the scandals. Because if you're Facebook and you're worth so much money, what, a few $100 billion? What does Facebook has worth so much money? Has your data. So their worth comes from the fact that they have your data. So if they don't sell it at all, they can't make any money. The only way Facebook is a big company is because it uses your data. Same thing with Google, same thing with Amazon. All these companies, they're big companies and they do well because they have your data, right? So this expectation that the whatever companies, whatever they do next, they're not gonna use your data, it's absurd. They're gonna use your data, okay? Apple doesn't have to use your data. They do because they can. But you could argue Apple can make a lot of money without using your data. Because even if they stop using your data, they sell super overpriced phones. Right? So people love their phones, right? And or whatever, iPads or something. And they could make significant amount of money by just selling those devices, right? I mean, if an iPad costs $100 to make and $500 to sell, they're gonna make a lot of money on it. But Facebook has no way to make money if it doesn't sell your data. If Facebook or YouTube or whoever doesn't sell your data, they are out of business. So that being said, how does Google knows the traffic? Your phone talks to Google, right? Your phone has an accelerometer in it and knows how fast you're moving and knows where you are because it has a GPS. Now you can easily tell by the law of variances that if I average a bunch of phones that are all in the same area, I could get a very accurate estimate of how fast the cars are moving. And then there's additional reporting, like people say there's an accident here or something that gets taken into consideration. That's why traffic estimation is a very easy problem because there's a lot of agents on the street that report the traffic. It'll be just you and me on a span of 300 kilometers. It'll be quite hard to estimate traffic, but if there's a lot of people, it's easy. But how do you take this traffic into consideration to estimate the shortest path of the runtime or the total time? That's a little bit hard, right? It's not a trivial problem, and especially not trivial to solve fast. Suppose the traffic condition changes suddenly. They do have an update, take this other road, is better, right? How do you do that fast? So there are interesting problems related to this, very practical problems. We want to move on, and I'm going to start something today, which we're going to finish next week. By the way, my intention is there's a class right before your, is that true? No. When's the last class? Do we have a class right before your exam on that Friday? Do we? I think we do. It's the last class on the 20th. So my intention for that class is to talk a little bit about something interesting that's not for the exam, so like half an hour. And then ask you guys in the middle of the class, do you want me to keep talking about this? Or do you want to make it a QA session? Like you ask whatever questions you want and I'll do my best to answer them if I can, okay? So we'll do it that way because some people would care more about the exam than about interesting things, right? That's reasonable. So here's what I want to do next. I want to do the last topic we have on graphs, which is network flows. But we can't really finish today, so we'll do a little introduction. And the introduction would really be explaining why network flows are not as easy as people think they are. So if you have seen this, you know why they're not, but if you haven't, here's the complication. What we want to show here, we have a graph, a VP, and it has a source, S, that's a vertex, of course, and a sink, as in kitchen sink. Okay, everybody's quiet. That's good. S. So S is where I really want to think of the edges as water pipes. So capacity on the edge is really how much water can you pass through. Is the volume of water per unit of time, say per minute. Right? When you have a pipe, you say how much water can I pass through this pipe per unit of time. Right? So this is more general than that. The network flows refers to more than water pipes. You can do much more interesting things with it. But for right now, our intuition is the graph is really physical in the sense that the pipes, the edges are really pipes to send water to. So here's the main thing that it's easy to, I'm going to draw a graph here. Maybe here. All the network flows algorithm is send flow little by little until max achieved. So that's how all these algorithms work. Our purpose is to, of course, send flow from S to T through the graph. So how does that work? Here's a graph which is a network, and I have these edges. Pipes are here are directional. D. So on each edge, I'm going to mark two things. The capacity of the edge, how much water per unit of time can go, and how much water, how much of that capacity I'm being used. So on an edge here, from U to V, I'm going to put two numbers, something like 2 out of 5. That means using two, what is this? We say volume waters in liters, or say gallons. If it's United States, right? Gallons. I'm using 2 gallons a minute. That's already being sent through the pipe out of capacity. Maximum capacity is 5 gallons a minute. So 2 out of 5 means I can send 5 gallons a minute, but currently I'm only sending 2. So here's an example, right? This is 2 out of 3. This is 1 out of 2. 1 out of 3. 1 out of 1. 1 out of 2. 2 out of 3. 0 out of 2. 2 out of 3, 1 out of 2, 3 out of 3. And this is an introduction. Next time we do this more formally, more like theoretical, so on and so forth. For now, I want you to form the right way of thinking about this problem. Everybody understands what capacity means? Capacities are fixed. They're not up to me. It's whatever how big the pipe is, okay? And it's some engineer decides this pipe has capacity 3. You can send 3, but no more than 3. So I cannot change the capacity. This is fixed. It's in some sense given to me. Maximum capacity you can use is 5. This number is up to me. I can decide how much water can I send through those pipes. That's completely up to me. So this is up to us. Capacities are given, so these numbers, 3, 3, 2, 1, 3, 2, 3, 2, 3, so on and so forth, they are given as fixed. It's never going to change. The how much water we send through the pipes, that's our decision to make. So how much flow am I currently sending from the source to the sink? Total, how many gallons of water are going from S to T right now? Every minute, I mean, because it's per unit of time. 3, right? Is it 3? We'll show later on that everything that comes out of the source ends up in the sink. Because that's how we formulate this problem. In reality, of course, you have a more complicated distribution network. If you're really distributing water through a city, you have the main sources where you have the pumps and the filtration and the water preparation. And then sinks are wherever the water ends up with. There are many sinks. But for the basic model, we have a fixed source and a fixed sink. And then we can add other sources and other sinks if we want to model a more complicated network. But for now, everything that comes out of here must end up in here. So it's easy to count the flow. How do I count the flow? Also, S has no incoming edges. And T has no outgoing. Again, this is a simple model. In reality, if you distribute water or food or packages, it may not be that simple. But let's take the simple model first. How do I know immediately what's the flow currently in the graph? If S has no incoming edges and has outgoing edges, and everything that goes out of S ends up in T. How? Where do I have to look? How did you guys come up with 3? I just measured the outgoing of edges of S, which are only outgoing. There's no incoming edge here. I look through this edge and say, okay, how much water leaves S? 2 plus 1, 3. I know for sure these 3 somehow must end up in there. That is, if the flow is correct. What does correct mean? So there's no leakage. I like that. So what would leakage mean? How do I detect a node or somewhere? Leakage will not happen in the middle of the pipe. Let's assume the pipes are not broken. But may happen in a node. How will I detect leakage? There's more coming in than going out. So let's write that property, no leakage. Every incoming flow, the sum over all the incoming edges, incoming to, say, this node U, right? Incoming to U. The sum of the incoming of this flow, let's just say F of U. Incoming to U, let's call this ZU. These are edges incoming to U. The flow on that node has to be, this is the incoming flow to U, and this is outgoing from U. That will be the sum over all edges outgoing, F of UZ. Right? F is this current value. This in here, 1 is the F on this SU. Is how much flow is currently on this edge. So similarly, this is UV, say, right? The flow in here, F of UV is 3. The capacity edge of UV is 3. Capacity, it's fixed. It's something given to us. We don't try to figure out capacities. Flow, we can do whatever we want with the flow. We can design our flow. Of course, the flow has to be, what's the relationship between flow and capacity? We can't send more water than it's possible. So the flow has to be smaller than capacity. That makes sense. So this is no leakage. There's nothing coming out, leaking out. Fine. So assuming this is correct, meaning every water that started to leave S ends up in T, no leakage. I know for sure this must up to 3. Right? If there's 3 gallons of water leaving, 3 must be going in here. There's no other way. Otherwise, somewhere water will be leaking out. Good. So I'm asking you, can I send more water if I want the maximum flow? Change the name of the chapter. If I want the maximum flow, can I send more? Is this the maximum I can do, 3 gallons a minute here, or can I send more?
They can increase capacity of.
So assuming I have already 3 water gallons flowing, so whatever pump is pushing those 3 gallons, I don't change those pumps. But I can push more if I want to. Can I?
Yes, you can.
How? I can push one here,
Intermediate.
here, and here. So this push notion will have to rely on some sort of route. I can't just look at this and say push.
Yeah.
That's not gonna work because what if this is saturated, some capacity? Like if you push it to here, it has to keep going, otherwise we have leakage, right? So I can't just say push simply because this capacity is not maximized. I have to look for a path, right? So to push more flow, we have to find a path. Find, we call it has a name. It's really an unfortunate name. I don't really like to use it. Path. Let's call it residual path. More like capacity, let's say the allowed path, allowing path. Unfortunately, the name it's being used there, it's augmenting path. Worst possible name, because augmenting means so many things. If I just say, okay, it's not network flow. If I come today to class and say what augmenting means, the word, you come up with all kinds of interesting philosophical things about what augmenting means, right? Augmenting is a vague word that can mean a lot of things. I prefer something like residual or allowing path that simply says, on this path, all edges have some capacity. That means I can push more water. Now, if I see edges that have different remaining capacities, in this path, every edge has how much water can I send? 1, 1, 1. But suppose this is 2 out of 4. How much water can I send through a path that has different remaining capacities? Minimum or less, but I can't beat the minimum. If the minimum is 1, I can't send 2 on that path. So now, this is the key introductory to this problem. Why is this not a simple problem? What's the maximum you can send from S to T, apart from this 3 that's already sent? So everybody saw there's a path through here. I can send 1 more gallon. That will saturate these pipes, right? It will be 3, 2, and 3. Can you send any more than that?
All the parts.
I'm just saying in this example, can you send more? Apart from this 1, 1, 1. If I do that, what will change? 3, 2, 3. Can I send more now? Is there a way to send more water?
You can send, but it will be lost in the leakage.
No, I can't afford leakage. There's no leakage. So these properties are staying as global properties until next Friday when I'm going to say, I don't want leakage, but I'm going to allow temporary storage. Like I'm going to allow a node to have some sort of reservoir. It's not leaking the water. It's storing it to push it later. Okay? That's going to be complicated. But for now, how much you get into a node, you have to send forward. Apart from this 1, 1, 1 that everybody saw, hands up. Did we see that I can send 1 more gallon here?
Yes.
Hands up so I can see them. Okay. Can we send more than that? Yes or no? So again, I send that 1 gallon to the top. I'm asking, can I send more?
No.
Really? I think you guys are looking at saying, if I try to, some edge is saturated, right? This edge looks saturated, right? This edge will be saturated. So even though I could send 1 gallon here, I can't send it forward from here, right?
Yeah, exactly.
So what was this tree here?
New password. We do the back.
Was this correct tree? Where is this tree coming from? It's 1 plus 1 plus 1, right? 3. So I argued that I can send more flow. So you guys says no. And that means the total maximum that can be sent is 4. I say I can send 5.
From S.
Huh?
From S. From the same starting point.
Yeah.
You can
Can we
send
change
it, but it's
the-
not reached even.
No leakage can be there.
No leakage.
Can.
What can I change?
That 1 of 1 can go from 0 to 2.
If I reroute this
Reroute.
water here through some other pipe, which is still available, I think.
0 to
I
1
send it here, and then
We'll change that
You
to 2.
send, you send it back up on 3 to 3.
if I say, okay, this water that's going through here, I'm going to allow it to pass here.
Yeah.
But then instead of sending it this way,
Send it.
I'm going to send it
1 to, yeah.
Down.
And then
Down.
you send it back up.
And nothing else changed.
then
No, we can change that to 2.
That
what's going to change?
We can
That
send
will
2.
be 1.
This is still a 1, right?
Yeah. No, we can change that to 2. So
Right, this is a 2 now.
That will be two.
Because this 1 doesn't pass through here, it passes here.
then that will be 2. We
And
can
so
send
that change will be, this becomes a 0. This becomes
One.
a 1.
1.
Yeah.
Yes.
And now in here I get only 2 because there's not, the gallon doesn't go this way. And then from here, I still have a 1.
Yeah, you can
Now
use
I
that
can
one.
send 1 more
1.
gallon to the bottom.
You alter the.
I altered that 1
Alter.
gallon, right? But as far as the pumps are aware and the sink is aware, they just changed the intermediary routing. So this is a critical point for max flow. If you look at this network, I want to put it back to what it was. 1, 0, 3. What we want to compute is called a residual network. So I'm going to draw the same thing and say, I'm only draw the remaining capacities, not the ones that are being used. So the remaining capacities were what? This is 0, right? This is, well, let's say we already sent that water flow to the top. So this is 0, this is 1, this is 0.
2.
1.
No, 2.
No, this one goes up.
1. 2.
And this is
1.
If I draw this network, can I found a path, residual path or augmenting path or allowing path to send more flow? No. That's the one that you guys looked at effectively, because you look at those differences and say, I can't find a way to send flow in. I can't push more water. The reason you can't, and I could, is because I had a different residual network. So this is simply the edge difference in this way, the remaining edges, so this is the residual UV. It's simply the original UV minus the flow. That's how you guys, I think, computed this. You say, take on any edge, how much capacity I had, subtract how much flow it went through, take the difference, that's the remaining capacity. I can't find any way to send flow in here. And how did I manage to push 1 more gallon? I rerouted some of the existing flow. That's equivalent to allow a more complex residual network. I want to allow a network that not just looks at how much flow can I send, which is obviously allowed. I also want to reverse or change some of the existing flow. So I'm looking at this edge, for example, 2 out of 3. And I'm saying, you can send the residual capacity 1 more gallon this way if you want. I think everybody can see that. What's the additional operation that I'm allowing to do here? That says not only you can send 1 more gallon because it's 2 out of 3, but you can also reverse some of these 2 that are already going. How do I reverse them? What does it, if I really have a water pump, what does really mean to reverse?
To send it somebody.
Do I really have to push it back and get it back in? There's a much easier way to reverse.
Stop the flow.
Not sending them at all. Right. So I want to allow a new edge residual that says reverse existing flow. So in other words, I want to say this edge is 0 because I have nothing left. But there is effectively an edge that goes this way now that says I can reverse this gallon that was coming this way. In fact, that's what I did, right? In order to allow 1 more gallon, the first thing I did, I rerouted this gallon here. And the way we model that is say there is now an edge of capacity 1 that was not existing in my original graph. This edge is new, right? This pipe doesn't really exist. Do you guys follow me here? I don't have a pipe from here to here. But because there's a gallon flowing this way, there is effectively a way now to send a gallon back. Now, in a physical water system, there is no pipe that goes that way. So the water can only flow this way. How do I reverse this? If I implement this in a real water system with pumps, I can't really push the gallon that way. What I can do? Not sending it in the first place, right? If I already send it, I could say effectively there is a way to send it back in physical terms, meaning I'm not pushing it at all on the pipe. So there is a capacity of 1 that's effectively a new edge here that's saying you can send this 1 gallon back. How about in here? There is a capacity going this of 3. Can I reverse that flow? Or in here, 1. How about here? There is an edge going 3 this way. That simply says don't send the 3 that, right? I could say conceptually I can send 3 gallons this way and 3 gallons back at the next round. But in physical implementations, I'm just gonna take the difference and say don't send nothing. How about in here? How about in here? How about in here? And how about in here? Which way this edge goes? The new edge. This is a new edge that did not exist there. It simply exists because there's a gallon flowing that way. I can just push the gallon back. So now if you look at this graph, the new graph, there's I think some combinations of stuff here too. If you look at this graph, you can see how I can send more flow. That has to allow to reverse some of the existing flow. I couldn't have pushed 1 more gallon without reversing this edge first. But if I'm allowed to say, okay, take that gallon that comes this way and reroute it, meaning push it back and then send it through here, now I can send more flow. So my only point for today in these problems, it's not enough to simply take the difference between capacity and existing flow and say, that's what I can send flow. We always got to look for more ways to send flow. That's the basic principle. Look for ways to send flow, and if you find one, send it, add it to existing flow, and eventually you get to the maximum. The only trick is, it's not enough to look at the edges and measure the difference. You have to allow reversing the existing flow, which means there are new imaginary edges here that were not really water pipes, but they correspond to reversing existing flow of the actual pipes. So this idea will allow us to discover the max flow. That will be on Tuesday. I'm hoping to get the midterms done today, but I don't know. I don't want to promise. If they're done today, you will get an email saying tonight they're available. But what happens is everybody's scheduling meetings. So if I finish them,